Welcome to Chem Help ASAP. Let's see a more complex example of how we decipher J values and multiplicity. Here is a spectrum of a small molecule. It has a CH2, and the signal for that CH2 is upfield, close to 4 ppm. The CH2 has one neighbor and therefore appears as a doublet. Looks good. The CH on the left also has one neighbor. It is a doublet and appears around 6.1 or 6.2 ppm. The middle CH has three neighbors. It appears at maybe 6.4 ppm, and what is this thing? Well, let's try to figure that out. Let's start with our CH2 doublet. The peak on the left is at 4.0920 ppm. The right peak is about 4.0678 ppm. The ppm difference is 0.0242 ppm. The simulated spectrum is at 400 megahertz. So 0.0242 ppm times 400 million divided by 1 million equals about 9.68 hertz. Round it to 9.7 hertz. So the peak is centered at 4.08 ppm, doublet, 2 hydrogens, J equals 9.7 hertz. Here is the doublet at 6.12 ppm. The left peak is at 6.1384 ppm. The right is 6.1036 ppm. The difference is 0.0348 ppm times 400 million divided by 1 million. That's a J value of 13.92 or just 13.9 hertz. So the peak is reported as 6.12 doublet 1H, J equals 13.9 hertz. Now let's tackle this signal. So this hydrogen has one neighbor on the left and two on the right. We already know what the J value is between these two hydrogens. It is 13.9 hertz. Let's draw this coupling. The hydrogen signal is split into a doublet, two lines. We'll make one red and the other blue. The separation in the doublet is 13.9 hertz. Now each of these lines will be further split by the neighbors on the right. We know this coupling. This coupling is 9.7 hertz. So the first neighbor splits the left peak once and the blue peak once. Now, that was the first neighbor. Let's do the second hydrogen. We're going to further split the resulting signals again. And let's do the same to the blue signals. This is split. The outcome of all these splittings All these couplings would be a pattern of 6 peaks with relative intensities of 1, 2, 1, 1, 2, 1. Although 6 peaks, this is not a sextet because a sextet would be 1, 5, 10, 10, 5, 1 based on Pascal's triangle. This 6-peak pattern does not fit with Pascal's triangle. Instead, the way to refer to this is a doublet of triplets. I use the different colors to highlight the fact that we have a doublet of triplets. Let's color our spectrum. To better highlight this doublet of triplets. Our pattern is not a simple one because we have more than one J value. To report this signal, we report the midpoint of the pattern, about 6.39 ppm, with its abbreviated multiplicity, a doublet of triplets, or DT, the number of hydrogens, 1H, and both J values. So J equals 13.9 and 9.7 hertz. This signal shows that neighbors are not always equal, especially when alkenes are involved. We can still report these signals, but we need to include all applicable J values. This was a quick example of a proton spectrum with a multiplicity that is affected by 2 different J values. Please like, subscribe, or leave a comment if you have any questions. Take care.